what I want to do is just increase your comfortability with solving differential equations, because all of quantum is diffie-cube. And I know you folks are definitely a bit more mathematically savvy than when I teach this. When I do 344, they're not required to take Calc 3, or it's like a co-requisite. Anyway, they don't know anything, so it's a real pain. So let's see. One thing I wanted to show you. This is just a kind of a slick introduction. It doesn't seem relevant, but it's going to be relevant next week, which is multidimensional. So I want to show you something. I mentioned multidimensional quantum is really easy. It really is. But I still want you to get a little bit of exposure to it before we actually do it. And to do that, and I'm also going to use standard mathematical notation. So again, you're in a test in diffie-cube, and you're given this. Solve it. What? Right. That sucks. Now again, if you're steeped into that world, this is actually the easiest question you could be asked. You know, one of the first things you would know, which of course is going to be hugely relevant, is that the solution is going to be some function. It's going to have an x and y in it. That's kind of obvious. But because of the way I wrote the symmetry of this problem is maybe a fancy way to describe that. The answer is going to look like this. It's going to be two separate functions. Now, you may be thinking like, well, but that would be true of anything. I'm just like stupidly writing the same thing again. The answer is no. What is not that? What is not that would be sine x plus y. Sine x plus y is not of that form. Sine x sine y is of that form. You see, when I did this, I actually eliminated, I guess technically, an infinite number of possibilities given the way math works, but anyway, you get the point. There are some things that will not conform to this, and I've eliminated them as potential solutions, and that's actually very useful. Okay, next thing. Again, mathematicians would know, they would know because, you know, kids are mathematicians and they take a bunch of classes, they know immediately to do that, and they also know immediately to do this. So that's why I'm telling you, you know, I always try to write the quantum stuff with the wave function in place, because when I see this, I'm like, what the hell, right? I mean, there's nothing in front of it, you know, that doesn't make any sense, but that's just how they write it. So that's a little sucky, and I find that a little disingenuous. Okay, so you should know to put the potential solution, and for reasons that I will show, and you actually do this on your homework too. I have you work a solution where it's like sine x plus y. I have you work a solution like that, and you'll see that this will not, that's just not right. Anyway, so maybe just for now, just trust me that the term for this is separable. Okay, so that's step one, is apply the wave function. Step two is, again, when you see this type of thing, apply the solution. So that's step one. Let me put a 1 by that. It's kind of important to make sure that you delineate this. The second step to solving this bad boy is then divide by the solution on the left. Okay, that's like, what the hell does that mean? Here, let me show you. It's very simple. Okay, f of x, g of y. Okay, so this is the left side, and f of x, g of y, and then you do that again. And notice that it's like, what's this, the commutation axiom of algebra? I forgot what this is called. And then this would actually equal a constant, right? So I divided through f of x, g of y. Now notice that I have the double derivative acting like a barrier between the two, but it should, because you can't just, you know, if this is a sine function, it may or may not jump over the double derivative. Double derivatives have ways of changing things, right? Okay, now what? Note that this is where you can see the consequence of the way I wrote the solution, f of x times g of y, because g of y will jump over the barrier. And f of x will jump over the barrier, the y barrier. The g of y will jump over the x barrier. And look at what you get. You end up with 1 over f of x, double derivative, f of x. Over here, same with g of y, the f of x is canceled. Here's your wall, here's your barrier, your y barrier. That keeps g of y inside on the right, and that's why it wasn't canceled. And that's still equal to a constant. Okay, now what you've done is you've proven what's called separability. So I didn't tell you this, but I wrote this down and I said solve it. The way to solve it is to start probing the question. The first probe was, is it separable? I didn't tell you I was doing that, but that is what I did. Is this separable? Hint. All of our questions in quantum mechanics, they're always separable, right? In math world, not necessarily. In quantum world, the answer is always yes. Okay, now what I've just done is I've proven separability. And what that means is, here's a bunch of x's and here's a bunch of y's. There's no intermixing, right? There's no, in this little term here, there's no y's, and in this little term here, there's no x's. If I can do that, I've separated them. Now what that does is that both are equal to a constant. And now you may recall when we were doing Planck distribution, we actually ran into this. I even showed you this then. I'm sure that's been lost, but fine. I mean, you've been overwhelmed with stuff. What happens is each term is itself a constant. See, the thing is, remember, these are different dimensions. And I don't even know what these describe. It describes my cat. This is the x and y is my floor. And the functions are the position of my cat as it chases a ball. Why would my cat turning left or right change the way whether it goes in or out? Why would those be, why would there be crosstalk? Cat doesn't know left and right from forward backward, right? So if these are not constant, for one of the reasons they're constant is because they equal a constant. But imagine that you'd say, no, this is like a constant plus x, and this is a different constant minus x. Sure, okay, that would actually solve this. If this is like cx plus x and this is cy minus x, the x's would cancel. That would be a solution. I can just tell you it's not going to happen. The reason is that implies crosstalk. That implies that when the cat moved to the left, it simultaneously moved forward, and it will always do so. No, there's no reason to think that relationship is going to exist. So so the next step is, now you're ready to solve this, but the way you do it is, and I'm going to forget g of y because it doesn't matter anymore. Okay, so I've got this. It's now equal to its own constant, and the same for y, where the original problem is actually got this going on. Okay, so again, each one of these terms is equal here. Let me just change this. Each one of these terms is equal to a constant. Each one of these terms is equal to a constant, and now that means I can solve it as such. The original constant is decomposed into the x and y parts. Now here's another thing. In math class, when you run into the situation, this has to be given. Just like I had to tell you that guy threw the electron to the right, the math professor has to tell you that. Has to give, you may think like, oh, this is 2 and that makes that 1 plus 1. Maybe, it just depends. I mean, it doesn't have to be that, but they do have to add up. Okay, next bit. I don't know what I want to say. Okay, now you can, actually it's, let me just drop this and let me do a specific example, because we're going to run into something that's going to allow us to solve the double derivative question. So here, I'm going to give you I'm just going to drop this for now. I just want to introduce, this is separability, by the way, and as we get further along, you're going to be doing this over and over and over again. So now let me kind of apparently go off on a different tangent, although although it actually isn't because all of this is the same. Let me work at a specific example. Also maybe to throw you off kilter and to show you that, of course, this is actually really quite easy. Okay, so let's solve that. Now, I can already tell you that it's obvious that there's separability, because if it wasn't, I'd have to have one of these terms. I'd have to have it. All right, so if there was an xy here, if that was ddx minus xy, not separable. That's a problem. If I had ddy ddx, not separable. All right, but I don't. It's obvious already it's going to separate. So I don't even really have to. I don't really have to go further with that. I can already show you. I already know for a fact that this is going to turn into this. And you can, do that on your own. 1 over 2y. So I won't do the algebra, but hopefully, kind of hope you can actually do it in your head, actually. Okay. Now, of course, the c is now going to be composed into two different parts. So this is equal to c of y, and of course, this is equal to c of x. Now, so we're going to drop c of y. We're going to drop the y. The x. This one is like a lot more interesting, right? So now I'm just going to keep working down. I'm going to solve that, and then I'm going to do one more example, which is basically a second order differential. Notice that that's a first order differential. That just means that I have ddx. A second order differential is double derivative of x. That's the second order. That's the ones that we always have in quantum because of the kinetic energy operator. You never get away from that. Kinetic energy is always there. It's always a double derivative. You always have a second order differential equation in quantum. You can't escape it. Okay. Now, I'm going to just solve the x. Forget y. X is a little bit more interesting. Notice that if you can solve x, you can definitely solve y, because x looks like it's a little bit harder. Okay, so, well, except one's first order, one's second order. Anyway. Okay, so what have I got? I've got 1 over f of x, derivative of f of x, minus x is equal to cx, where again, cx had to have been given to you. What you then do, now that you've proven separability, multiply everything by f of x again. And that gets it back into a form that's a little bit, makes you a little bit less cross-eyed and a little bit more what you're used to. Cx, f of x. Okay. Now you got to solve this SOB. And, oh, by the way, just to give you a hint, the answer is going to be like e to the x squared. Right? Can you see that? The derivative of e to the x squared is going to be x e to the x squared. X e to the x squared minus x e to the x. Anyway, so hopefully you kind of can see that. You can see that's coming. Anyway, but I'll prove it. Okay, now, note that what I can do is I can factor. I don't know what to do with this, but I can actually factor the f of x out on the right. So I just brought the f of x over to the right, and then I factored it. Now what I can do is this. I'm going to have the partial of f of x equal to cx plus x. What I'm going to do is, you've seen me do this before, I'm going to take the partial of x over here, and then I'm going to divide by f of x. Remember how, you've seen me do this before, it's not that bad. Remember I told you how you can play with partials like a juggler. You can bounce them around, like a over b. A over b equals c, therefore a is equal to b times c. Right? So you can do that. And then, well, we're almost done. Now you integrate it. Now, who recalls what the left side? That's actually a very standard. What's the integral of x to the minus 1?
Oh, that's the natural log.
Natural log, right? You knew this? You remember? Now, who says that f of x is an x? right? Now, just because I know I have the change of a function, you may be like, well, hold on, it's got to be x or y. Well, maybe it is, right? So the point there is just ignore it. It's just natural log. It's just natural log of f of x. There you go. See, I know maybe there's some limits and constants of integration. In physical science, that those are always zero. So anyway, its integral and that's an easy integral to solve. But what you end up with is f of x is e to that integral, which would be what? 1/2 x squared. Yeah. There you go. That's the answer. And you can plug that in to the original to this thing, and it'll work. It'll work. I actually do that on my notes, but I think we're kind of out on time because I'm horrible at time management. Yeah. Okay, tell you what, now what about the other guy? What about the y? The second order differential equation. This guy is crazy. You may think that there's going to be this simple trick to that one, but here's the thing. You can kind of see like, I guess you're gonna, I'm probably gonna be able to do something like this. You actually can't. So this way that I juggle df dx, I can't really do that when I've got a double derivative. That doesn't work anymore. It just is. It sucks, but it is. You actually have to do second order differential equations by a completely different way. Okay, so now let's do a second order differential. And so it'll be like the y problem, but I'm just going to actually start calling it, I'm just going to use letters of x, because you're kind of used to x, used to solving problems with x in it, and not so much y. So anyway, so how do I do that? Now, I swear to God, this is so wacky that it takes me a little bit of time. Hopefully I won't completely bomb it. It always takes me a little bit of effort to figure that out. Okay, so let's do this. What do I want to do? Let's solve this one. And again, let's write it out as a mathematician would. Solve that. Now, what we're going to be able to do is show you that what I'm going to get to is the general solution. A e to the ikx plus b e to the minus ikx. That's actually the answer to this, by the way. But we're going to do it in the math, like, with math speak. Okay, I swear to God, I have to stare at this for a while because I get a little bit off on this. Okay, so what I'm going to do is, God, how do I do this? Let's say, okay, double derivative plus, now this is going to seem really, really, really strange. Okay, so I've just done some obvious work and I've turned it into this. But I'm still like, well, what the hell do I do with that? This is the part that's like nuts beyond belief. And I just can't get over how, I don't know how anyone ever figured this out. Okay, I'm going to write this a very different way. I can put a constant in front of this. I'll just make it 1. I'll say A, double derivative, A times a double derivative, plus B times a single derivative. What's B? 0, but it can still be there. And I'll just change that minus to a plus. C can be negative. Am I doing this right? Technically, I guess I should have an f of x. Oh, anyway. Yeah, you see? This is still that, as long as I absorbed the minus into C, which is not a big deal. B is 0, A is 1. I just generalized it. That's what I've done. So this is a general second order differential. But notice that this looks just like a times r squared plus b times r plus c equal to 0.
It's the characteristic equation.
Or the,
Auxiliary.
anyone know another, what's the solution for r? I'm using r for a root, by the way. And there's two answers to this equation.
Yeah.
No, hold on. Think 5th grade, swear to God,
E squared, I squared, something. It's like the
d squared plus or minus,
square root of
right?
4ac all over 2a. It's the quadratic equation.
The quadratic equation. The solution is the quadratic equation. Question? Huh? B squared minus.
So it's negative b.
Yeah, negative.
Negative.
Oh, negative b? Oh, here,
That's
maybe
where-
it's
not B squared.
in my notes. Yeah.
Negative b.
Negative b. Right. Sorry, yeah. I do have it right in my notes. I'm just trying to do it from memory. Okay, now here's where this is clever. I've made r the root. It's no longer the double derivative, it's the single derivative. You see, I've turned this second order into a first order because what I've done is I'm looking for the solution. This is our problem. Remember that I wasn't able to put the dx squared over on the right and then divide the double partial of f of x by f of x. That's junk. That's mathematical junk. It's meaningless. You can't be doing those games I did in this game you can't do that with this. It's junk. But look what I did. I've turned this second order into a first order so long as it has these roots. This is, right, r squared, this double derivative. The problem is actually a single derivative squared, but I've got the solution to the single derivative. Right? See that? Yeah? I know it's a little, look, it's really kind of mind-numbing and I still don't think I fully understand it. But again, I want to point out, I was able to easily solve this using the natural log trick, but it was reliant on my ability to juggle the partials around. And then divide df by f and get a natural log. Anyway, blah, blah, blah. None of that works for a second order differential because it's junk. But by using the quadratic equation, I made, this is actually this is the single derivative squared. And I know I can solve single derivatives, and I know that that's what it is. Okay, so what does that mean? Remember, I got an r plus or minus. What it means is I've got that's what it is. Now I know how to solve that. Here, let's put in my f of x. And what you end up with is, see now I can play the game. See my point? And then I just integrate it. And there you go. Yeah, we're almost done. Here, let me go ahead. I mean, at this point, it's just trivial. So the problem with the second order differential is, I just said it ad nauseum, so I'm not going to say it again. What ends up happening is to turn it into the friendly single derivative form. You know, it's not a double differential, it's a single differential. Single differentials are incredibly easy. I mean, there it is. That's the solution. It's incredibly easy. The consequences, though, is that you don't have any possible constant. You're limited to what is there. Okay, so what you end up with is, you end up with f of x is the integral. So you actually end up with a linear combination of this r plus dx. See, another thing is that you have two solutions. So two things is you can turn it to a very easy first order differential equation as long as you accept the fact that you only have two roots here, and the answer ends up being a linear combination. So the answer is is a double, is e to the integral of these things, which again is really just not that bad. How are we doing on time? Okay, yeah, I got just enough time to actually make this relevant. So right now, I know this is probably just a confusing jumble of letters. So now let me turn f of x into a wave function, the constant into energy, and yeah. Actually, wait a minute. I think I made a mistake. I made a slight mistake there. It's not, no, it's e. No, I made a mistake. Let me bring this back down. Sorry. I'm kind of speaking out of my rear end here. It's not like, sorry. That's one solution. It's not on top, it's on bottom. Right, so anyway. And I'm not quite sure how they know that, but anyway. So, yeah, that's what I meant to do. So, my bad. Well, in all honesty, I don't know that this is the worst. Okay, so when I say that when I have the integral of two potential roots, the consequence of there being two potential answers is that you end up with e to the integral, but you have two of them. And anyway, all right, so last bit, let me see here. Okay, now let me turn that into a wave function. I've got to figure out, okay, so I've got, and I'll make this as hard as possible. I'm going to throw everything at you. Double derivative, wave function, and let's include potential energy. Why not? Let's make it as hard as possible. This is similar to what I wrote in the last hour, except I just put the potential and energy on the left side as opposed to the right side. Okay, now what I see from here, to morph this into the problem we just had, I have A is equal to minus h bar squared over 2m. B is still 0. There's no first order differential. There's no ddx. There's the double derivative. And C is minus 3. Wait a minute.
B minus E?
Yeah, B minus E. Yeah, B minus E. Actually, I did this with B equals 0. B minus E. Yeah, okay, sorry. My notes actually have a mistake. Okay, so now let's figure out what R plus and minus are. Let's do R plus. Okay, B 0. 0. Plus square root of B squared
0.
minus, is that right? Minus, I already forgot. Minus 4A C over 2A.
Which is negative h bar squared over n.
Okay, now let's see what this is. The 4's cancel. Let's see, I've got the 2m's, I feel like, here, I gotta not confuse myself. I can take the minus out by putting an I. Now I've got 4 R squared times 2m over minus oh, okay, I see. So it's I. Okay, the two's cancel, so I end up with 2m b minus e over h bar squared. Right? And that's a minus sign?
Yes.
There's a minus sign. And then our minus is oddly plus. Is that right? I just feel like the plus should be plus and the minus should be minus, but it looks like
It's
it's
minus 4AC.
minus. What?
Since it's minus 4AC, it's the A is on the minus, so it's a positive 4. Because A squared over 2A is already.
Wait, so there's no minus.
Under the square root.
No, there's a minus sign there.
You're missing a minus sign.
In the
for
square root,
A.
there's two minus signs, from the A and from the original minus.
So that's plus.
Yeah.
Plus?
Yeah, just that.
Minus 4. Yeah, you're right. Well, now hold on, I think something's wrong here because, no, this can't, hold on. Come on, time. Sorry, folks, I should have had it all together. I got 2 minutes left. Okay, what have I done wrong? I think I'm just not translating this from minus b, I shouldn't have erased this, that was stupid, b squared all over 2a. A is definitely minus h plus a, 2m, minus c.
Yeah, so the difference between R plus and R minus is there's a negative where between the 0 and everything and the square root.
And so the problem I have is,
Is C the right value?
the problem I have is that I should have a minus sign in the square root.
You're gonna root it with I.
No, hold on, all right, so the problem is where's my I? I'm lost, I'm completely lost.
You can pull a negative out of the B minus E and make E minus V.
Yeah, you can factor.
And then you can factor a -1 out of B minus E.
Right, I could do that.
And then it'll be,
That actually would be quite simple. Right?
I'm not a mathematician, I'm an engineer.
Yeah, look at that, yeah, that's a clever trick.
But I'm bunch.
Yeah, that's how you do it. Right, because E is usually higher than B. E has to be
Exactly.
higher than B.
Ta-da.
So that's why that makes sense. So the image end up with is I 2m E minus V
Yeah, there it
or
is.
H bar squared. And that's our plus and our minus is going to be minus I.
Yep, square root, same thing. But that's my hat trick for the day, ladies and gentlemen.
Okay, and therefore the solution is e to the minus, e to the integral of that, but that's a constant. So that ends up being I root of 2m e minus v.
Call this K.
Right, that would be k. Well, we already know that's k. And the integral of a constant is just x, but because there's two potential solutions, you end up with a sum.
So each one individually or the summation of the two.
Yeah. Now, so, and the way you figure that out is, as you're gonna see, the way you're gonna figure that out is, you have to have a boundary condition. You have to, it's in the setup to the problem. So, like in the finite barrier that we're gonna finish up on Monday, the A and B are figured out only because of the way I set it up. Because I set it up with the particle initially moving towards the barrier and with a certain amount of energy, that is how you figure out A and B. So right now, you can't whittle this down any further because you have to have more information to solve it like we'll do on Monday. Anyway, okay, then here we go. All right, so